Okay, everybody, good morning. I hope the social dinner went well. Welcome to the last talk in the series presenting the content of Mathlib. Our speaker is Michael Rothgang about differential geometry in Mathlib.
Yeah, good morning. I'm glad you're already here. I hope your brains are kind of working because let's do some lean together. Well, thank you all for coming here, and thanks for the organizers for making this wonderful event happen in this beautiful location. It's a pleasure to be here. So let's do differential geometry. You know what Mathlib is? What's differential geometry? You might say it's a study of smooth manifold and their associated structures, such as Lie groups, Riemannian metrics, or semi-Riemannian if you're a physicist. Symplectic manifolds, you can study foliations, vector bundles, etc. Sure, but what is a smooth manifold? I'm not going to assume you know this, so let's start with a picture. So imagine you're a person walking across the surface of the Earth, or perhaps you're an infinitely small insect, like a really small ant walking across the Earth. Then you know that wherever you are, you can walk in two directions. You can move forward and backwards, and you can move left and right. And if you're really, really small, well, you don't notice that there's perhaps hills and crests. For you, everything looks flat. So wherever you are, the Earth looks like a disk to you. So of course, Earth is a disk, right? Well, not quite. But Earth is a shape. The surface of the Earth or the surface of a potato is a shape that locally looks like a disk. And that's an interesting mathematical object. We call that a two-dimensional manifold. Okay, so let's make that mathematical. What is a manifold? It's a topological space. And you ask that, well, locally, around each point, you have an open set, which is homeomorphic to an open set, an open ball in Euclidean space. And if it's homeomorphic to R to the n, then you call your manifold n-dimensional. So surface of the potato is two-dimensional, just to realign is one-dimensional, the space we live in is three-dimensional, and so on. So this locally homeomorphic means each point has a coordinate chart, so an open set and a homeomorphism into the open ball. And then whenever you have two coordinate charts and their domains overlap, then of course you also have a coordinate change between them. And we ask that the coordinate change, that always will be a homeomorphism, but if they're actually always smooth, then we call the manifold a smooth manifold. So let's do some examples. So the first one is the empty set. It's a manifold of any dimension. Don't laugh, this is actually important. So for my PhD research, it's extremely important that the empty set is a manifold of any dimension. Because if you know you have a manifold and its dimension computes to -3, you know it must be empty. Zero-dimensional manifolds are just isolated set of points. For one-dimensional manifolds, you can have the real line, of course, or you can have a closed interval. Or you have circles, or of course, unions of those. In general, if you have just Euclidean space, you can take an open disk in there. That works. So if we're in dimension 2 and onwards, so the Euclidean plane works, the sphere works, what we can also do is take the torus. So take a donut or take a coffee cup. Actually, don't have a coffee cup next to you, but imagine your favorite coffee cup. And that is a two-dimensional, the surface of that is a two-dimensional manifold. But that's not all. You could take two donuts and you can squish them together so you have a thing with two holes. And well, that also is a manifold. Or you do that not just 2 times, but any number of times. And if you do that n number of times, well, we call that the closed genus n surface. So you find a little picture here. And also that's a smooth manifold. So actually for zero manifolds, one-dimensional and two-dimensional manifolds, you can even make an explicit list. You can say, okay, you give me a manifold, and then I can decide like which item on the list it is, and we can prove these are all. In 3 dimensions, it's still possible, but it's already extremely complicated. So the Thurston geometrization conjecture essentially solved that problem, and the proof of that got Perelman a Fields medal. So extremely deep and complicated. what in dimension 4 onwards? Well, you can prove that the classification is mathematically impossible. So the world of manifolds in high dimension is getting really wild. So do we have some basic? You can do configuration space in physics and engineering, and that might lead you to symplectic geometry. All of these are different examples of what manifolds are. So the upshot is you have a quite easy local intuitive picture, but the global shapes can actually be very interesting. And perhaps to give you an example, what's not a manifold, the letter X is not a manifold, because somewhere in the interior you would think, okay, it should have dimension 1, but at the intersection of these two crossings, that doesn't work, because if you take a neighborhood of that point and take out the middle point, then you get 4 pieces, whereas for a manifold you would just get 2. Yeah, okay. Everyone with me so far? Great. Everything looks nice and simple now. Let's make it more complicated. So I told you about the open disk. What about the closed disk? I mean, that is not a manifold in our sense, because if you take a point on the boundary, you take an open ball around it, you're outside of that closed disk. But it's almost something similar. So you have points in the interior, and then you have an open neighborhoods which are homeomorphic to an open ball. Or you can take points on the boundary, and they're homomorphic to the upper half of an open ball. So we can also study these things, and these are manifolds with boundary. But then, of course, we can make them more complicated. What is if you take the product of the manifolds with boundary? Well, then you also have the corners. And yeah, that's, for instance, like if we take the unit cube in n dimensions, then, well, you have interior points, you have boundary points, which are in the interior of the faces, but you then also have like vertices, or perhaps you have the corners of the cube. Yeah, and here the local model is not just the top half of your Euclidean space, but you're modeled by some Euclidean quadrant times your Euclidean plane. And actually it does not end there. So let's make a step back and imagine we're God, we're the maintainers of Mathlib, and we get to decide what different definition of differential manifolds do we merge in there? How should we choose the right definition? What should we pay attention to? So if we have a good Mathlib definition, what are good criteria here? So one item that's perhaps a bit on the meta level is the number of prerequisites required. If there's 2 equivalent definitions, and one requires formalizing an entire zoo of things before I can even state it, and the other one is doable today, and they're both equivalent, we might want to start with the doable definition. So Mathlib has elliptic curves, for instance, and the current definition we have is defined on, depends on a cubic equation. You could also do a fancy one using schemes, but we don't do that yet because, well, the elliptic curve definition that we have right now was doable back when it was attempted to do. Of course, at the end of the day, you want to show both definitions are equivalent, but you need to make one thing the definition and the other one, well, proven to be equivalent to the definition. The second one, it should be ergonomic to work with. Like usually, even if you fix on, that's my mathematical definition I'm going to use, there might be 1, 3, or 5 different ways of saying the same thing in Lean. Last week, we were going through 5 definitions of the same mathematical object just to figure out which one of those was nicest to work with in Lean. So there is some experimentation, and you do have knowledge from experience, but it takes a while to find this definition is the best one. And you might also start with one definition and realize we need to change it to a different one, and then, well, you change it. So it should be ergonomic to work with. And the third one is generality. So there are different opinions on the scope of Mathlib. Some people say like all mathematics should be in there. Others say, well, it needs to match what the maintainers know. But I think everybody agrees that all modern mathematical research should eventually be in scope for Mathlib. So if I do a definition, it should be sufficient to express all the uses of, say, manifolds in modern research. So if you publish a paper in a top journal and it uses manifolds, Mathlib's definition should have you covered. Otherwise, the definition is not good enough. And in particular, this means we lean very heavily on abstraction. because this allows reusing results. Like usually in a paper, the most interesting things are the little lemmas that you're going to use for your paper about an entirely different topic. So if we want to prove a lemma, we want to prove it in as much generality as is reasonably possible. And the same applies for definitions. If I can take the same definition, weaken its hypotheses, and get something that's still equally useful, we're going to take the weaker one. So these are some very general considerations. I could probably have said the same about any field. So what does it mean for manifolds? What constraints do we have? So, well, the first one is we want to allow for different notions of smoothness. We want to have perhaps topological manifolds where you require your transition maps just to be homeomorphisms, or perhaps C2 manifolds where transition maps are C2, or you want smooth manifolds, or you can also want analytic manifolds, and perhaps you also want to be able to deal with piecewise linear manifolds. If these are exactly your thing, like we want to have you covered, so we need to allow for different kinds of smoothness, different kinds of regularity. Then we need to allow for boundary and corners, and that's not just because these are natural objects to state, but because we actually need them to do research. Like if you're a differential topologist, you will remember that there's a classification of one manifolds, that a compact one manifold has an even number of boundary points, and that's extremely important for some pieces of theory. But if your manifolds don't have boundary, you can't even state that. Or you want to do borders in theory, that's also a classical subject that still has modern applications. Or you want to actually state the geometrization conjecture that Gottperl-Fields medal, whose proof Gottperl-Fields medal, but actually stating the classification of three manifolds, well, you also need to talk about boundary. So you need to have a definition of boundary to even be able to state these groundbreaking theorems. So we obviously want to have manifolds with boundary. And then you want to be able to take products, and saying we have boundaries but not corners just makes your life miserable. So we also want corners. Then what you also want more generally is to allow different base fields. So when I told you manifold is locally homeomorphic to R to the n, those are real manifolds. But of course, we can also do complex manifold. And if you're a complex geometer, you will care about these. But we might also care about, say, p-adic Lie groups. So if you're working on Fermat's last theorem, you will need those at some point. And while p-adic Lie group is, well, a group that's also manifold, so a p-adic Lie group should include a definition of a p-adic manifold. So a definition should allow the p-adic numbers. And certainly not everything will work over all fields, but a lot of the general theory will generalize, and we should state it in as much generality as we reasonably can. And then the last big item is actually infinite dimensions. So there are different definitions of infinite dimensional manifolds with different trade-offs, but it's very clear that you want to have infinite dimensional manifolds at your disposal. For instance, if you have two CK manifolds, the set of all CK maps between them is actually very nicely behaved infinite dimensional manifolds. And you need to study that for some proof. So for instance, my field of PhD research, symplectic geometry, heavily depends on using the implicit function theorem on infinite dimensional manifolds. Like the foundational papers in the field just don't work at all if you don't have this. So we want Mathlib to support you in infinite dimensions. Okay, so how do you do this? How do you formalize this? How do you formalize manifolds with boundary? So that's perhaps one mathematical insight in Mathlib that's a bit interesting. So smooth manifolds include several data. You have the manifold itself. Say, for an example, let's take the closed unit disk of the Euclidean plane. Then you have a topological space where it's locally modeled on for manifolds without corners that might be R2. In this case, it's the upper half plane. So you're an open set, like you're locally homeomorphic either to a ball, so to say, the upper half plane, like away from the x-axis, or you're homomorphic to, well, an open ball that intersects the x-axis. So you have a topological space, which is the local model. But then you also want to include boundary, and you want to be able to do calculus. So if I tell you, well, this map is smooth, and you just have this topological space, then you need to say, what does it mean for a map from the upper half plane to the upper half plane to be smooth? And it's a bit annoying. It would be much nicer if you could just talk about maps between norm spaces because we know what smoothness means there. So what we choose is also a norm space and a continuous map from your local model into the norm space, which in this case is just a canonical inclusion. And that allows you to talk about smoothness. You just, well, take your manifold. Yeah, well, you take your map from the manifold to the topological local model and then into the norm space. And then, well, now you're in business. Okay, and then of course you need to pick charts on the manifold, and there's also a little design thing on Mathlib here. So on paper, what you'd usually do is you have a collection of charts that all together cover each point. So in Mathlib, what we also fix is a choice of preferred chart at each point. So just for each point, you choose globally one and for all, say this is my favorite chart, and we record this information. That doesn't preclude you from using other charts, but we make this choice once for convenience. So whenever you're at a point you need to pick one chart, you're allowed to say, pick my favorite chart, and you have the shortcut available. And then the final piece of data is the proof of compatibility that for any two maps in your atlas, in the collection of all the charts, the transition map between them lies, well, it's a homeomorphism or smooth or it's analytic. And the way we abstract that is through the notion of a structure groupoid. So basically the saying, like the transition maps have this nice property, which is stable under composition restrictions and so on. So the structure groupoid could be, for instance, all smooth maps, or homeomorphisms, or analytic maps, and so on. Okay, so that's the mathematical explanation of how a manifold looks like in Mathlib. Do you have any questions about this? Do you have one?
Do you want I to be injective?
Yes. Yeah. And if the manifold has no boundary, we also want it to be surjective, and also have so we also want an inverse from the model with corners range to the definition. So it's a partial equivalence on the, yeah, very good question. Okay, so if you're fine with the mathematics, let's look at the lean a bit. Okay, so let's say M is a manifold modeled on a topological space. So like both M and H are types, and we ask that both of them, each of them be a topological space. So how do you formalize charts at manifold? So the naive definition would be the following. We say, well, a chart for M is a homeomorphism between open subsets of M and open subsets of H. So we say, like, let S be an open subset of M, let T be an open subset of H, and then the chart is a homeomorphism from S to T. Yeah. So note that in Mathlib, charts go from the manifold into the model space, but you also have inverses of charts. So whichever way your textbook went, Mathlib has you covered. You just need to decide in one direction, and Mathlib decide to go from the manifold into the model space. So the naive definition of charts would be homeomorphism between open subsets of your domain. But this would actually be rather unpleasant to work with. So if I have a chart around the point P in the manifold, and I want to apply it to the point P, to even do that, I need to always pass a proof that P is in the domain of the chart. And I need to do that every single time I want to use it. Like if you want to apply the chart to a point P 3 times on one line, you need to put the proof 3 times, not just once. If you did it on the previous line 5 times, no luck, you need to repeat it. So it gets quite annoying and repetitive quite quickly. So that's perhaps just a little example. So we have an open set S of a manifold, one open subset of the codomain. We have a point in M that lies in S, and we have a chart. So what we want to do is apply the chart and get a point in a manifold H. So let's try just applying that and see what happens. Okay, so we take phi, we coerce that to a function, and then we apply P, and this one errors. And Lean actually gives us a quite clear error message. Why does it not work? Well, because the argument P is a point in the manifold, but the domain of phi is not all of M, but just a subset. So this will not type check. What we can do instead was we can construct a point in the subset by passing P and a proof that rely in P. Sure, you can do that, but you need to provide a proof just for this notation to make sense. And similarly, okay, now we have a point, and that's kind of the result, right? So let's just return that. Well, that will also not work because the return result is something in a subset T and not something in the manifold M and the local space H. So you need to here apply this. Just look at the underlying value of this. So you see, I mean, there's friction both applying the chart and actually getting to the manifold. And doing that all the time, you could do it, but it would not be ergonomic at all. So what's the solution? Well, we use a pattern that we've seen before. We use a junk value pattern. So charts map the manifold, all of the manifold to all of the model space, but we only prescribe the behavior on a certain open set and target. Like outside of that, they can do whatever, and we will not care about the precise value. We just know we can just apply it at first and then use that we're inside the domain of this chart whenever we actually want to prove any meaningful theorem about it. Okay, so perhaps the first definition here is a partial equivalence. So that's saying, so between two types, and that's saying, well, we have a function. So it's a function from an open set of one type to the open set of the other type, together with the choice of inverse. And well, then the type of a chart is called an open partial homeomorph, and that's a partial equivalence from an open set of the domain to an open set of the codomain, and we ask that both the map and its inverse be continuous on that set. So this is how to do charts, and well, now a manifold is a charted space, so we ask that around each point we have a partial homeomorphism to a model space, and we call it a choice of preferred chart. So I kind of told you about this, but this is how to make it rigorous. So we take two pieces of data. So we take an atlas, so just a collection of all the charts that we care about, and a chosen preferred chart at each point. And then we want that each chosen chart actually lies in the atlas, so they're somewhat related, and that actually the chart at a point X, also is a chart around X, not just some totally unrelated chart. So two very reasonable conditions, I'd say. So this is like the first part of defining a manifold in Lie. We have a charted space structure. Now a smooth manifold is, well, a charted space structure, so that for any two charts, the coordinate change function between the charts is smooth on the common domain. And this is how to express this condition. So we take two charts, and well, then here we take the inverse of the second chart and we compose it with the first chart. That's a map on the model norm, on the topological model space, so it's a map on the model space, and we ask that this map be smooth on, well, the domain of this map. Yeah.
Perhaps you can say, I don't know if you introduce the stop symbol.
I haven't. Yeah.
Parsed as omega, by the way.
Yeah.
And also maybe right. The composition is the other one. Yeah. It's not the way you compose two functions here, it's not with the F composed with G, you apply F and then you apply G.
Yeah. So, I mean, if you do composition, you always have this tricky question, which way does your composition go? And I think the algebraic topology and the category theory library also have different conventions there. So we're picking the right one.
This one is the one of category of the same thing. Yes, you apply A dot C and then you apply.
I think so. I mean, there's only one answer that type checks, and this is the one. Yeah. Yeah, so this is saying, well, this coordinate transformation map, we're saying that it's smooth on the domain, and the way to say smooth on the domain will say condiff on. Then here's the field over which we're working, the real numbers, because say here we're doing a real manifold. And the stop says the regularity. And actually, when I'm saying smooth, I'm lying slightly. I'm saying it's even analytic. Yeah, so as I said, we have like smooth, analytic, and CK integrate into all one definition. Okay, so the way to capture this is a predicate called has groupoid. So that's saying, well, yeah, let's look at that briefly. So we say, like if we have a structure groupoid, that's basically something like saying like smooth transition maps, and then we'll charted space has that groupoid if for any two maps in the atlas, the transition map actually lies in that groupoid. And now structure groupoid itself, I mean, the prototypical example you want to think of are just CN maps. So you have a set of open partial homeomorphisms, like all the open partial homeomorphisms which are CN on that domain, for instance, and then you want that the property of this is stable under composition, under inverses, the identities in that groupoid, and that your property is actually local. So you can show smoothness by showing it at each point. So again, that's a very abstract formalism, but the point is that this allows you to speak about PL manifolds, analytic manifolds, conformal manifolds, TK manifolds, all of these in one definition. You don't have to repeat the same thing 3 times over. Okay. Yeah, so that's basically what I've told you here. We have the structure groupoid, that's the common abstraction around CK or analytic or PL or conformal or whatever manifolds. And perhaps the one you care most if you just want to do CN manifolds is called condiff groupoid. So all of this was, we didn't mention boundary and corners yet, so the way to encode this is a model with corners, that's how we call it in Lean. So it's a map from the topological model space into a norm space of our base field. And say, if your manifold has no boundary, then you just take the identity map. But say, you could also have the model with corners on Euclidean half space, and there's just the inclusion from the like closed upper half plane into your Euclidean space. And there's other models with corners. Yeah. So for instance, this here is a standard model with corners on Euclidean 3 space. Or that's the model with corners on Euclidean half space, but there's more examples. So if you want to say let M be a smooth manifold, here's the most general definition. So we take a base field, we take a norm space in which we're modeling things, we have to take a topological space in which we're modeling things. Then we need to choose a model with corners that tells us, okay, how do boundaries and corners embed? And then the real bacon is this one saying is manifold. So M is a CN manifold with model with corners I. Yeah, I agree it's a little verbose. I can talk about later how to make it less verbose, but this is how to do that. In practice, what I always do is I copy paste the same lines, and you got used to doing that easily. And I mean, for now that will work, and a better solution will come. Yeah, so assume we have 2 manifolds like that. Here's one M, and here's a manifold N, like both of the same field K. And then we have a function between them, so we can talk about differentiability. So the way to say that F is Cn, well, you might say, so it's continuously differentiable, so you arrive at cont diff, but you also have continuous differentiability between norm spaces, and this is about manifolds. So we call this one cont M diff, where M is for manifolds. So this one is saying that F is n times continuously differentiable. And then you need to specify the choices of model with corners to work with that. Because the way we do smoothness, well, we have a function from here to here, so it's smooth at this point. How we do that? Well, we look at the preferred chart at this point and the preferred chart at this point. And if we compose with that, we get a function from the model, topological model space to the topological model space. And then we apply the models with corners to give you a function between norm spaces. And then you can talk about smoothness. So that's the definition we have. But this depends on the model with corners you have. So naively, you just need to make it part of your definition. That's why we have a model with corners. But then, I mean, in 90% of the cases, it's quite obvious from context what the model with corners is. So we have some special notation that allows you to omit this. So instead of writing cont mdiff, you can just write cmdiff and leave out the model with corners. And Lean will try to figure out the model with corners for you. And if it can't do that, well, you can still go back to just writing the longer thing. So this is how to say f is cn at a point x. Well, it's cont mdiff at. Or you can say f is differentiable on S, well, then you call it, well, not differentiable on, but m differentiable on. Again, it's about manifolds. The model with corners here, that's the function, and that's the set S, which is differentiable. And for all of these, we have notation. So this is how to state it in short. So m differentiable, this like square brackets and then the set, you're saying it's m differentiable on that set, and that's the function. Okay, so we can talk about differentiability, but we also want to do a derivative, right? So we have deriv and f deriv for function between norm spaces, and then we have, well, mf deriv for function between manifolds. So if I have a function that's differentiable, well, then the derivative at a point is a function between the tangent spaces. Yeah, I will not tell you in detail what these are, but basically the notation is again mf deriv, then you need to put the model with corners again, the function at the point. And there's actually another case of a junk value design. So what do you do if you have a non-differentiable function? You could say, yeah, derivative requires a proof that your function is differentiable each time we talk about it, but that's the same issue. Like you need to prove differentiability once, and then you need to provide the proof 10 times. That's not as fun. So what we do instead is saying, well, if the function is not differentiable at x, we just set the derivative to be 0. So then you can at least formally write down that statement, and then, of course, all interesting theorems will need to take hypotheses as things are differentiable. So for instance, the chain rule is such an example. So suppose f is differentiable at x, and the function g is differentiable at g of x. Well, then g of f is differentiable at x, and we know what the derivative is. It's a composition of the derivatives. And well, that's how to state the chain rule. Yeah.
So, two questions. On lines 132,
Yes.
have you used m differentiable add instead of m diff add for any reason or just for pedagogical reasons?
I was telling you the long form, so I can also show you the short form. I mean, it's quite easy. You just delete things, and things still work.
And then a similar question is.
And that's actually also a notation for the MF deriv. So you need to put a % sign to make it ambiguous that you're just not missing arguments. And then you can also leave out the model with corners here. Yeah, okay.
And concerning tangent space, do you have the same thing? So is there something like T space that can take M as a?
Not yet, but it would be easy to add.
And I think it would be great. I mean,
I think so. I mean, I have a list of all the, so basically you have all the definitions that mention a model with corners. So of course you want to have notation that allows you to omit it for all of them, but you need to write it for all of them. And somebody needs to say, I review it and merge it. Yeah, so.
You can ping me if you want.
Okay. Yeah, that's a custom elaborator. I'll mention that in a moment. Okay, so you had a third question, you said? Okay. So then let me go back to the presentation. So we had a little tour of differential geometry. So let me perhaps give you a bit of an idea. What's in Mathlib already? So with smooth manifolds, we have the Fauché derivative, we have the chain rule, we just saw those. Then we also have some classes of smooth maps, so for instance, diffeomorphisms, local diffeomorphisms, smooth immersions, smooth embeddings are almost done. We have products and disjoint unions of manifolds. We know the classification of zero manifolds. And we actually have some examples such as Euclidean space, Euclidean half space and quadrants, real intervals, but also unit sphere or units in Lie groups. We have a nice theory of topological and smooth vector bundles and basic constructions about them. So we can talk about smoothness of sections. We can talk about smooth bundle maps. We have the Lie bracket of vector fields. We know about Lie groups and the Lie algebras, also over any fields, not just the real numbers. Then we have smooth bundle metrics and Riemannian manifolds. We also have existence of integral curves, local flows, and their smoothness. I mean, all of this is the work of many different people. I mean, I guess Sebastian Gruzel is the person who really started this and did a lot, but I think there are about 6 names that I would really need to mention to make a complete story. Let me perhaps just say that Winston Yin, who's sitting here in the audience, actually proved the last 2 items, and also this one here, units and Lie groups. So some of these people are real and they exist and they hear you and you can talk to them. It's not just a sterile topic where you go and then you leave and somehow it persists, but actually there are actual people who care about this and who care about this today. So what's missing? Special maps. So immersions, embedding, submersions, we want to have the definition and all the basic theorems about them. Smooth submanifolds and subbundles are missing. Quotients of manifolds and gluing. We want the implicit or the inverse function theorems, not just on norm space, but on manifolds. How about the regular value theorem? Or the fact that Riemannian metric actually always exists. And if you care about differential topology, you might do Sart's theorem, or want to classify 1 manifolds, or actually 2 manifolds, like this classification of spheres is beautiful, but it should be added to Mathlib. And also, we don't have a good theory of smooth fiber bundles, for example. But luckily, I mean, some of these are actually in the making. So there is a group who's working on quotient manifolds, and I'm hopeful that, well, we'll have them by the end of the week. I think that's very doable. Yeah, great. So we know about the existence and uniqueness of the Levi-Civita connection that's almost done and in progress. We actually have connections on vector bundles, and well, we also have lots of work on defining submanifolds. It's just not all merged into Mathlib yet. And well, there's also a bit of other work such as oriented manifolds, Bordism groups, the inverse function theorem, Sart's theorem, but also orbifolds or differential forms. But all of these have a lot of work done, but they also can use a little help getting it over the line. So if you care about differential geometry and you don't know what to do, talk to me. I have ideas what you could do. Okay, so it's all peachy and we just need to wait. Yes and no. So yes, of course, that will work. But no, there are some challenges here. So the first one you already saw is type classes. Let M be a manifold is 3 lines. If M is a manifold, the next 4 lines show you let E be a smooth vector bundle over M. I think we can agree that's a bit too wordy to just live with that all day, right? We also have verbosity. Like, let M be a Cn section, so let M be a section of E that's Cn at a point X. This is how to say this, the smoothness. 1 large line of lean code. I think this is not good enough. We have a challenge of invisible mathematics. Because we're using, like if we were using subtypes, this would be extremely painful. Because of the junk value pattern, it's not as painful, but we do have lots of trivial proofs. This point lies in that set. And of course, it's hard to compete with invisible proofs. On paper, you never write these down. Like you write this down perhaps in a differential geometry 1 lecture for the first 2 weeks. And then if you're a student, you check this every time on paper, but you generally don't write this down. You know it checks out and that's it. But of course, lean doesn't let you get away with skipping proofs. You need to prove it every single time. And that is a bit too annoying and too painful. But again, this is a challenge of mathematics, not a challenge of lean. on the mathematical front, so also can we find better abstractions? So we do have definitions like being smooth at a point within a set, and these are mathematically useful, but they're also quite low level. Are there higher level abstractions that we can find? Is there a way to formalize saying, this is just a local argument, so we can check it in norm spaces? I think we can have still room for improvement here. And perhaps the last one is combinatorial explosion. So if we have 4 kinds of differentiability, often we want to state each lemma 4 times, like prove it for the lowest level version first, then deduce it for the higher level versions. Then, of course, if we have a statement about the n functions, we probably want the same for differentiable functions. And perhaps also analogs for norm spaces. So from 4 lemmas, you might easily end up at 20 versions of the same lemma. And sometimes you also want to have an applied or unapplied version. So if you, for the rewrite tactic that matters, and then you might end up at 40 versions, like in the worst case. This is, I mean, of course, it's a bit of the worst case that I'm illustrating here, but this is not entirely hypothetical. I had one pull request of 50 lines that became 5 PRs of 250 lines because I was adding the same lemmas 5 times. Or another real-life example, working on the Levi-Civita connection, when I had 1,000 lines of what we did was just copy-pasting code from CN functions to differentiable functions. Sure, I mean, it's a PR that's quick to write, it's also a bit enjoyable. You can do it in the afternoon when you're a bit tired. You don't need to really think hard, but it would be much nicer if we didn't have to do it in the first place. So what can we do? So for type classes, there is actually a solution. There is an open PR doing it, but Mathlib is not yet usable with it because, well, my theory is that it needs a bug fix to lean core. So if I could make a wish to lean core for differential geometry, I'd actually like 2 changes to be merged. So the first one is this improved class breadth by Joven Gerbscheid. And the second one, well, should actually be merged first, that fixes some exponential behavior and unification. And my hope is that after that, Mathlib will be actually usable with that change. You can do differential geometry nicely, and well, you can also do unbundling and make Mathlib another 30% faster. Would be quite nice, right? You can write custom elaborators to reduce the verbosity. So this one was a detail kind of glossed over. But you can also, that's the second one we saw, inferring the model with corners automatically. So my vision is that you almost never have to write that by hand. But of course, it's optional. If it doesn't work, you can just write the expanded version. So X is the CN vector field at X. It was one huge line. Now it's just this short expression. I think that's quite readable. And in a similar vein, you can also make funprop work. So if you have a composition of smooth functions on a manifold, right now you need to do everything by hand because funprop can't guess the model with corners. But we've written code here to guess the model with corners. So it's relatively easy to just make funprop support that. And then it's easy to say this function is smooth on a manifold. Yeah, you can use tactics to auto-generate lemmas and keep API in sync. Let me perhaps skip over the details here and just, well, give you 3 takeaways. So finding the right definitions is hard mathematical work that is independent of any theorem prover. That's work that Bourbaki were doing when they were doing filters. We need to do similar things for manifolds. And in fact, well, our definition in Mathlib is more general than any textbook that I'm aware of. Second one, invisible mathematics matters, and formalization actually makes it visible. So I need to think about managing it nicely. And the third one, tooling matters for making formalization ergonomic. Well, thank you for listening.
Thank you. So we are running a bit late. So just one quick question while Damiano set up his laptop. If there is some remaining question. Okay, nobody. So we already had some questions with the talk. So thank you, Michael, again.